All right, let's get a move on. We spent an entire week and a couple of days actually on that orange packet and getting the concepts down about what the fundamental theorem is. Sorry, Ryan. So let's go on. We're going to take a look at some other purposes of the integral, and you're gonna come up with a bunch of properties for it as well. Okay, so let's identify something here. So this thing that you see here, okay. Now you'll notice I put f of x here. This right here is called a definite integral. It's called a definite integral. Later on in this unit, we're going to talk about indefinite integrals as well. Okay, they end up not having these limits on the ends here. Okay, so the answer to an indefinite integral, okay, because this is actually a direction. It's telling you to do something. It's telling you to integrate the function f of x on the interval from a to b. And the answer that you get from it is a number, okay? Some real number. Could be positive, could be negative, could be 0, and so on. Okay? So just getting down a couple of things. Well, if you think about what we've just done, this definite integral relates to area. Okay, relates to area. And there was a magic moment, which is actually really kind of cool, that happened that again changed the world, because BC, before calculus, area formulas were, all of the geometric shapes that were put together by Euclid. So we had circles, we had squares, we had rectangles, triangles, okay, trapezoids. Every one of these things were either a polygon, okay, or they were a circle. They said, if you want to find the area, hey, have we got the area for you? Okay? So they came up with all these formulas. Pi r squared, trapezoid, h over 2 times the sum of the bases. Just plug in what you do and you get the answer. Okay? But now, after calculus was created, it's a very, very clever thing. Watch. If you had a parabola, okay, y equals x times x minus 4, negative x times x minus 4, and you said, what's the area of this? Before calculus, people would be like, well, you can't ask us that question because we don't know the answer to that. Because that curvy thing, that parabola that you're drawing, isn't a polygon. It's not a circle. Can't be done. So these area formulas that we had for a long time didn't apply to this. And people said, well, how do you figure the area that? And you said, well, I don't know. I can give you an estimate, and they try to figure out ways to estimate it. But now, with the power of the calculator of calculus, we can say, well, wait a second. If you integrate from 0 to 4, on the function negative x times x minus 4, you can get an answer. It's the actual area. And we're actually separating ourselves from the fact that this has anything to do with an increasing function or that this is the derivative. Now we're saying, well, wait a second. You can use this formula to get an answer for an area that previously would have been impossible to do. Okay? All right, punch in your calculator, everybody. Get me an answer. Tell me what the answer for that area for that parabola is. Yes. I'm amused by simple things. Now, if this was a question on the AP exam, you can do it however you want. I'd probably, if I was doing this one, I'd probably say, all right, this is doable just straight from here. I'd go to math, FNINT, plug in a 0, plug in a 4, plug in negative x times x minus 4 dx, and answer 10 2/3. Get that? Okay. That's probably the fastest way to do it. And so we can say, I know the area of that. It's just 10 2/3. Boom. There it is. Okay. Now, if I did a different question where I said, let's consider y is equal to the sine of x on the interval from 0 to 2 pi. Okay. Actually, I'm going to put this on the front board here. So, go find me the total area bounded by, come on, there we go. Follow me. So if we said y is equal to the sine of x on the interval from 0 to 2 pi, okay, and what I'm asking is 1, 2, 3, 4. What I'm asking is, what is the total area if I add up both of these? Okay. I want you to write me an integral that tells me what the total area is. I want to know what this and this added together are. Okay. Now, it's as if I don't care about positive or negative area. What I want is, I want whatever this is plus this is. And pretend I'm making, I've got concrete or carpeting, or it's a grass field or whatever. What is the total area of those two things? Don't have it relate anything to increasing and decreasing. Yeah. Yeah. Yeah, so here, we can think of this, what we've done for the last week and a half is we've said, okay, this thing that we're integrating is a derivative. And it shows you the net change in the function, the antiderivative. Now we're saying, wait a second, this relates to area too, where we can put in any function that we want to and ignore the fact that it has anything to do with the derivative, and it can actually produce areas for us. Mm-hmm. Right. Okay, well, I know how to do this. This is easy. I learned this last week. Start, stop. Got it? Everybody get an answer? 0? I don't believe you. Don't. Come on, we've been working on this for so long. How can you say that? Wait a second. So if I want to use this for area, it gave me 0. Well, wait a second. This is symmetrical, so this has the same area as this, right? But this one, according to the integral, is positive, and this one's negative. Here's the deal. Just like Christina was saying, if we want to now apply the integral to do area, we have to be aware that it doesn't know the difference between the positives and the negative areas, and it's thinking that it's doing something that has to do with increasing and decreasing. So we have to be careful with this. So this gives you an answer of 0. Okay? That's not what I want. Okay? So somebody write me an integral. Tell me what an integral would be that would work. Absolute value where? Okay, around the sine of x. Still go from 0 to 2 pi? Okay. You're telling me what to do here. 0 to pi of okay. Look at that, everybody. Is it going to give us the correct answer? Oh, this one, that's my bad. Yes. Okay. We're going to start, what we're going to do right now is understand that there's many different ways you can find this answer and you would still be correct. Okay? This is correct. This will do it. And what is the answer? What did you get for an answer? 4. This will give you an answer of 4. Okay? There's a little bit of overkill on the absolute values, but that's okay. It still works. It still answered my question. Okay, somebody else. Bailey, what do you got? Just like that? Is that correct? Yes. Now, before we go on, just to make sure you understand it, by taking the absolute value of the function, you're saying, okay, I know that this is the sine of x, but y equals the absolute value of the sine of x looks like this. Because it takes this and it makes it positive. That's the absolute value function. So when you add these two up, you get the 4. Yeah.
Is that saying if you take the integral of something that isn't differentiable, it makes it continuous?
It's got to be continuous on the open interval, but it does not have to be differentiable. You can do absolute value, stuff like that. All right, so far so good. Let's do a couple more. What do you got?
From 0 to pi, sine of x dx times 2.
Okay, sweet. So watch this. Does everybody agree that if I go from 0 to pi of the sine of x dx, what is that answer going to give you? 2. If I multiply this by 2, by putting a 2 in the front of the integral, It says take 2 times the answer, whatever you get for this, and this gives you an answer of 4. That's correct. We're just getting started. Give me another one.
Just like number 2, but instead of the absolute value around the sign of x, you put it around like the whole integral.
Okay. So that's a good question. Same exact one as number 2?
But you put the absolute value like on the outside of the integral.
Okay. Instead.
Oh, I do like this separate.
Take this off and then put it around the whole thing?
I like the 2, and then in the middle too, that is plus sign. So like each of them, yeah.
Ah, I see what you're doing. Okay. Is this correct? Okay. The answer to this side, inside the absolute value is 2. So the answer is 2 there. The answer to the inside of the absolute or inside the integral here is a negative 2, but that forces it to be 2. So 2 plus 2 is 4. That's correct. Okay. By the way, what if we did this? Okay. Would that work? No, that would still give you 0. Okay. So where you place the absolute values matters. Okay. Anybody get something else? Yeah.
Go from pi to 2 pi, just like number 4, but -2.
Okay. So pi to 2 pi. So pi to 2 pi of the sine of x dx, and then multiply by what?
Negative.
-2. Everybody see what he's doing there? If you take the second half of the normal one, you can multiply it by -2 and you can get the answer. Every one of these is correct, right? There's nothing wrong with any of them. Yes. So if we do this, I'm going to just modify this one. If we could take this one right here, take this one right here, there, and change this to a minus. Agree? Okay, what about this one? Yep. Key here is that this has a lot of symmetry. In fact, there's 4 sections that are all the same size. So that ends up working. Okay. All right. Now we actually demonstrated a whole bunch of properties here that we're going to actually write now. We're going to write those right now. So let's go do this. So properties of definite integrals. And I'm going to throw a couple of them at you that maybe we didn't cover yet. So here, properties of definite integrals. Definite integrals. Okay, so we're assuming here that the function is continuous. So this is kind of a big deal. Why does f have to be continuous if we're going to integrate on it? Has to be a closed shape. Okay? If it's not a closed shape, yeah, we could have a problem here. So like the function went here, and then it jumped over here, and we said, oh, find me the area bounded by the curve in the x-axis. Okay? You know, we got a problem. Okay? So the function has to be continuous, or else you got a major problem. All right, here's what. Do not say it out loud. This is the integral from, well, you read it. Don't say it out loud. Tell me what this is. Stop and think about what it means. Okay, answer? 0. Why? By definition, a point, if you start at A and you end at A, that means it's the area under the point. By definition, in geometry, a point is just a position in space which takes up no area. Yes?
Could you also look at it as f of a minus f of a?
Sure. That's another way, a great way, that would be a good proof. By definition of the fundamental theorem of calculus, this is f of a minus f of a. Way to go. Okay, here's one for you. Now normally we go from A to B on an interval. You can still imagine that we're going from A to B. Okay, got some random function here. But I'm asking you to go from B to A. Where here, maybe we should note here that, that B is greater than A. Just like this picture. Think of an answer, think of a problem, use your calculator to prove it. Think of an answer, think of a problem, think of what you think the answer to this is, and then validate it using your calculator. Mary's demonstrating the properties of gravity. Okay, who's got an answer? Yes.
Nothing special, nothing
Exactly the same. As what?
as if you were to go from A to B.
From A to B? Okay, so I'm going to put this up here. This is what is out there. This is a situation. Kendra? It's equal to the negative of this one? So you mean they're opposites of each other?
Yeah.
I'm hearing confirmation there. Okay? But just because people agree on something doesn't mean that it's right. Remember that. Kendra, why is that? Okay. Yes?
Can't have a negative area.
Can't have a negative area. Okay. I know where you're going with that, but it's not good enough.
Instead of f of b minus f of a, with f of a minus
All right. He's on a roll. What does this one mean right here? It means f of b minus f of a, correct? Right? What does this one mean? It means f of a minus f of b. That's what we learned in the fundamental theorem of calculus. Are those two the same? No. But if you take the opposite of this one, they're the same. Okay. So this says you have to, if you go backwards, you have to take the opposite of it to have it equal if you were to go forwards. This, knowing the fundamental theorem of calculus helps to justify this, okay? Can anybody think of it in terms of a function that's increasing or decreasing? What this means on an interval, from A to B? Amy? Everybody be thinking, what does it mean if a function is increasing and we're doing area to state where it's increasing or decreasing? Stop and think about what it means. Okay.
So, in the fundamental theorem of calculus, I think B minus F equals essentially the y coordinate of the second point multiplied by the y coordinate of the first point.
Correct.
If you're going opposite, then it would be the negative sign.
Okay, be just the opposite. Very good. Okay, I'll say it one more time, one different way. If a function was increasing from A to B, it's decreasing from B to A. See that? It's just a matter of how, it's the multiple perspectives that help you to understand why something is. Okay, we're going to do another work day tomorrow on explaining this stuff. You can start that next assignment. There's actually not a lot of work there. All right, have a good day.